Hello everyone. Let us now look at Module 12, Mechanical Systems. In this module, we explore the fundamentals of mechanical systems in Revit, focusing on ductwork, pipework, and the settings that control how these systems behave. We begin by reviewing mechanical settings, including hidden line display, duct and pipe conversion rules, offsets, slopes, and size definitions, ensuring system behavior aligns with project standards. We examine duct types, fittings, routing methods, placeholder ducting, and how systems are generated automatically or manually. We also review duct sizing tools, including friction, velocity, equal friction, and static regain methods, along with branch sizing constraints. The module also covers insulation, lining, and the importance of system verification through tools like the System Browser. We conclude with an overview of mechanical pipework services, flange behavior, fitting rules, and pipe sizing. Together, these concepts form the foundation of creating accurate, coordinated, and analyzable mechanical systems in Revit. In this exercise, we continue from the partially completed system created in Module 9. Our goal is to complete and correct a mechanical supply air system, resolve connectivity issues, verify sizing, adjust ductwork, and use the system inspector to check performance. Let's begin. Section 1, completing the duct system. Step 1, open the starter file WFPRME12 Mechanical A. Step 2, navigate to the ground floor plan and zoom into the area near grids F2 to E3. Step 3, select the two middle duct branches that have open connections. These appear as darker blue. Step 4, in the type selector, change their type to flanged radius bend/shoe branch. Nothing will visually change yet, that's expected. Step 5, now select each branch and drag the end of each duct away from the center line of the main duct, pulling it back to the external face. This forces Revit to trim the branch back and apply a shoe connector, joining it to the main duct. Step 6, select both shoe fittings at the ends of the branches. Step 7, in the Properties palette, ensure loss method equals coefficient from ASHRAE table. This is essential for accurate pressure loss calculations. Section 2, splitting and preparing the main duct. Step 8, from the Modify panel, choose Split Element. Step 9, split the main duct 2000 mm to the left of the FCU connection. And again to the right of the FCU connection. These splits prepare the duct for size reduction. Step 10. Check the duct connecting into the fan coil unit. Ensure its offset matches the offset of the main duct. Offsets sometimes change, so always verify. Section 3, Duct Sizing and Adjustment. Step 11. To size the entire system, hover your cursor over any air terminal and press Tab until the whole system highlights. Click to select it. Step 12. From the Analysis panel, click Duct/Pipe Sizing. Step 13. In the Duct Sizing dialog, set Branch Sizing, Larger of Connector and Calculated. Click OK. If a warning appears, cancel it. This usually happens when Revit cannot align a T due to geometric differences, typically because a duct was not split. Our previous split prevents this, so you should see no error. Section 4. Cleaning up connection points. Step 15. Now we tidy up an unnecessary union. From Modify, select Trim/Extend to Corner. Step 16. Select the two duct segments adjacent to the union so Revit merges them into one continuous duct. Step 17. Select the leftover rectangular union and delete it. Running the System Inspector. Step 18. Hover again over the system, tab until everything highlights and select it. Step 19. Open the System Inspector from the Analysis panel. If the button is missing, it means there's still a connectivity issue that must be resolved. Step 20. With System Inspector active, move your cursor through various parts of the system. Revit displays the flow, static pressure, and pressure loss of each segment in real time. Editing System Performance. Step 21. To test the system dynamically, select a section of duct while System Inspector is active. Step 22. Use the options bar to modify its width, height, or offset. Step 23. Notice how each dimension change instantly affects the flow, static pressure, and pressure loss. Step 24. When finished testing, click Finish, then cancel to exit the System Inspector. Rebuilding the system if errors occur. Step 25. If the System Inspector button is missing, the system must be rebuilt. In the ground floor plan, select the entire system, then press Delete. Step 26 to 28. Ensure the taper, slip joint is also removed. If necessary, delete it manually. Recreating the system. Step 29. Open 3D View, System 3D to confirm the flex ducts are connected properly. Step 30. Back in ground floor plan, select the air terminal without the taper slip joint. Step 31. From the Systems panel, choose Duct to begin creating a new system. Step 32. In the Create Duct System dialog, System Type, Supply Air, Name, Mechanical Supply Air Room, 2, tick, Open in System Editor, click OK. Step 33. Select the air terminal to the right and add it to the system. Step 34. Return to System 3D View. Step 35. Select the air terminal missing a flex connection. Drag the flex connector to meet the terminal and ensure the diameter is set to 224 in the options bar. Final check in System Browser. Open the System Browser and confirm that all terminals and the FCU are now part of the Mechanical Supply Air Room 2 system. Selecting any component in the browser will highlight it in the model and vice versa. This confirms the rebuilt system is valid, connected, and ready for performance checking. That completes the Module 12 exercise. You've corrected branch connections, set loss methods, split and sized ducts, rebuilt broken system relationships, aligned flex connections, and performed a full performance analysis with the system inspector. These skills are essential for validating mechanical systems in real MEP projects.